webcast discusses situations where energy gets transferred either into or out of a physical system. And we're also talking about a new visual tool called an energy conservation diagram. So first, let's just recall that when we were talking about energy pie charts, we were talking about systems that were isolated. And because the system had no interaction with other systems outside of itself, the amount of energy in this system had to remain constant. In other words, the change in the energy, that's the delta E, had to equal 0. Now the energy could redistribute, so energy that belongs to a system is stored internally in these storage modes. It can be stored as kinetic energy, gravitational potential energy, elastic potential energy, and dissipated energy. But for example, if the gravitational energy reduces, then maybe kinetic energy increases. But the sum of the four amounts of energy has to be constant if the system is isolated. And we were using pie charts. The pie stayed the same size because the amount of total energy was the same. Well, now let's talk about situations where the total energy does not stay the same. Maybe it increases, maybe it decreases. So because a physical system's energy can change when it interacts with a system outside of itself. And commonly, that interaction is due to a force that one system exerts on another. So there are actually 3 ways for energy to transfer into or out of a physical system. We're primarily going to talk about the first method, which is called working, and we'll represent that by an uppercase W. Working is a process by which energy is transferred through external forces. As a simple example, when I hold a rubber band in the palm of my hand, it is relaxed. But if I take my finger and pull on the rubber band, I cause it to be stretched. And so now the rubber band has elastic potential energy that it did not have before. So I have applied a force by pulling on the rubber band, and in applying that force, I transferred energy into the rubber band. There are 2 other methods of transferring energy. One is called heating, where energy transfers from a hotter object to a cooler object. And the other is radiating. For example, our sun is always sending out electromagnetic waves, and when they pass by the Earth absorbs some of them. So that is energy being transferred by the process of radiating. Okay, but again, we're primarily going to talk about work. So we'll use the word work to refer to an amount of energy that flows into or out of a system. And its work is accomplished by one of the systems applying a force to the other system. And just to be careful in the way we're using our language, the force is the method of transferring energy, but forces themselves do not contain any energy, right? The energy has to belong to a physical object, but by that object either exerting a force or by receiving a force, the object's energy can change. So now that we're talking about systems that are not isolated, systems where the amount of energy may get bigger or may get smaller, the delta E, which is the change in energy, will no longer be 0. And the change in energy is going to equal the sum of the working, radiating, and heating that's done on the system. Now, the energy will still be stored internally to the system as kinetic energy, gravitational potential energy, elastic potential energy, or dissipated energy. But the total amount of the sum of those energies does not have to stay the same anymore. If work brings energy in, then the sum is going to increase. If work takes energy out, then the sum of those energy storage modes will decrease. Okay, in order for the energy of a system to change, there has to be an interaction with an external system. Okay, so now we're going to go to worksheet 6E and talk about energy conservation diagrams. This is a method of analyzing systems where there is an energy transfer. And so first I want you to look at this energy conservation diagram. In the center there is a circle, and this is where we are going to show what we are considering to be included in our system. It's the way we've defined the boundaries of the system. On the left and right of that circle, there are two bar charts, and these are where we're going to show how the energy is stored internally to that system. And we can go ahead and label, because energy can be stored as gravitational potential energy, as kinetic energy, as elastic potential energy, and as dissipated energy. Okay, so I'm going to go ahead and put headers here on these two bar charts. Okay. So notice that the bar chart on the left, it says this is for position A. This corresponds to the first, so position A corresponds to the first place that we look at the system, and position B corresponds to a later time when we look at the same system. And so we're going to describe how energy has redistributed from when it was at position A to when it was at position B. And then below this chart, we will write the conservation energy equation. Okay, so in our first example, we're looking at a toy roller coaster, and the cart of the roller coaster has been pushed against a spring. So right now the spring is compressed. The cart is not yet moving, so the cart is not moving, and right now it is on the ground, right? It has no height. But then when the cart is released, the spring pushes the cart and it starts moving along the track, and it goes through this loop-de-loop. So at position B, we're looking at it at the top of the loop, and so now the spring is relaxed, right? It's had time to go back to its equilibrium position, but the cart is moving, and it is much higher, right? It's above the ground. It's not on the ground anymore. Okay, so the first thing we need to do is to identify how we're going to define what's in the system. And right now I'm just going to put everything that I see in the system. So there's the cart, there's the track, the spring, and the earth. We almost always include the earth in our system. The reason that we do that is so that we can talk about changes in gravitational potential energy without considering the work that is done by the earth exerting the gravitational force on the object. Okay, so in general, you will always include the earth in the system. Okay, so as I look at this system at position A, and I can just go through the list of ways that energy could be stored. There is no EG because the cart is on the ground. It has no height. There is no kinetic energy because the cart is not moving. There is elastic potential energy because the spring is compressed, and that's a reversible deformation, right? It's going to go back to its original shape. There is no dissipated energy. We never show dissipated energy in the first view. Okay, so at the beginning, all of this system's energy is stored as elastic potential energy. Now, at position B, the spring is relaxed, so there is no more elastic potential energy. It is higher, so there's some EG. It is moving, so there's some kinetic energy. By the way, in this problem, they're telling us that the track is frictionless, and so I will not be showing any dissipated energy. And so I'm going to show some gravitational and some kinetic energy. By the way, if you look at this bar chart, I started out with 5 blocks of elastic potential energy. And so over here on the right at position B, I want to show 5 blocks of energy, right? Really, this is an isolated system. There is no interaction in the way we're looking at it. There's no interaction between the system, the way we've defined it, and anything external to it. And so energy is conserved. I should have the same amount at position B that I had at position A. Okay? And so now I'm going to write an energy conservation equation. Now, I don't usually do this next thing, but I'm going to do it right now for the first one. I'm drawing a red dashed line through the middle of the circle. In the conservation equation, you always want to say that everything on the left of that dashed line equals everything on the right of that line. So in this case, we have elastic potential energy in the system at the beginning, and that amount of energy is equal to the amount of energy that's stored as gravitational energy and kinetic energy at position B. Notice that I'm putting these little triangles. These are deltas because we are talking about changes in energy. The amount of elastic potential energy at position A, it changed. In fact, it all redistributed to other storage modes, right? So the change in the elastic potential energy equals the change that we saw in the gravitational energy plus the change that we saw in the kinetic energy. In part B, we're looking at exactly the same system. In real life, the same thing is happening. It's a toy roller coaster. A spring is compressed. When it's released, the spring pushes the cart and it goes through the loop-de-loop. So what's happening at position A and position B is exactly the same as what we were looking like. But now we're going to define the system in a way that does not include the spring. Okay, so our system now will be the cart and the track and the earth, but it does not include the spring. So, since the spring is not part of the system, I can't have any energy now stored as elastic potential energy. And so at the beginning, the cart and the track and the earth, they're not moving, they're not above the earth, so they really don't have any mechanical energy. But at the end, they still have the gravitational and kinetic that we were talking about, right? The cart is at the top of the loop-de-loop, and it is moving. And so I have these 5 blocks of energy in the system that weren't there at position A. Where did they come from? They came from the spring, which is now outside the system, applying a force to the cart. And so that's what we mean when we talk about work. So the system has more energy at position B than it originally had. Energy was transferred into the system by the spring. And so I'm going to draw an arrow coming into the system. I'm going to put the letter W next to it because the way the energy was transferred was by work. And so now the conservation energy equation is that the work that was done on the system equals the change that we see in the gravitational energy and the kinetic energy. So exactly the same thing was happening in part A and B, but by the way that we chose to define the system, we're looking at it in a slightly different way. But again, exactly the same thing is happening, right? It was the spring pushing on the cart that made it move down the track. But in part B, I'm considering the spring to be external to the system, and so I'm thinking of that as energy transferred in by work, whereas the elastic potential energy was originally part of the system the way that I had it defined in part A.